Hello, so today our lab will be looking at multiple regression. So this dataset is a little silly, but hopefully it's on theme for Halloween. We're looking at vampires and different variables that might predict the number of vixens that vampires are able to seduce. So these are all the variables that are in your data set that's posted. And we want to know if attractiveness, so that's this attract variable, and number of castles owned, this castles variable, predict the number of vixens they're able to seduce. So for today, this pre-lab video will mostly be going over how to get the output for MRA. MRA has a number of assumptions. Some that we can test for and some that we can't. For example, we can obviously look at what the sample size is, though that's more of a rule of thumb. But there's no test for whether you have all of the variables in the model. Okay, so we're going to start by looking at just how you run a basic regression. So everything's here, but I'm going to walk you through it as well. So once you get to this screen, you want to put in what your dependent and independent variables are. So for here, our dependent variable, the one that we're trying to predict, is the number of vixens. Our independent variable are attract and castles. Next, we'd want to go and click statistics to see to change the options that are indicated there. So once we get this up, only the estimates in the model fit will typically begin with being marked off. We also want the R-square change. R-square is a measure of how much variance the model explains, and that's relative to how much variance there is to explain in the first place. So, for this situation, R-square change would be measuring, well, how much variance is there in the variable vixens, and how much variance are we able to explain once we add in attractiveness, and how many castles they have. We also want the part and partial correlations. So this is to help see how well the variables are correlated. Part and partial correlations are special type of correlations that essentially don't include the variance that's explained by other variables in the model. I believe you'll be talking about that in class. If you're confused about what part and partial correlations are by the time the lab is next week, let us know. It's easier to explain with some visuals in a conversation. We also want to click off the collinearity diagnostics. So these will give us the VIF and the tolerance. So for VIF, we want that to be less than 10. We want the tolerance to be above 0.2. So they both tell you the same thing, but that helps us with that multicollinearity. So for the residuals, if you don't know, residuals means it's how much the individual scores, individual people, are away from the average trend line. So the distance between the trend line and the individual scores is their residual. So the Durbin-Watson's is looking at the independence of errors. So that's saying that are all of the error terms for these variables independent of each other? For our Durbin-Watson, we want that to be, the result's going to be somewhere between 0 and 4, and we want the value to be around 2. We also want case-wise diagnostics, and this will just find you outliers. You can put in different values for the standard deviation. So I like to use 2.5. 2.5 standard deviations away from the mean represents approximately 1 in 100. So that seems like a fair size given our data set. If you want to be even more careful, you could have 3, 3.5, whatever you think works. I like having it a bit lower because then I can see the ones that might be a bit higher and decide if I think that they're outliers. Okay, so the next thing that we're going to be looking at is under the save. Okay, so when we look at this, typically what you'd want to save here, so when I say save, this is meaning that these values will become variables in your data set. Typically, we want the residuals. Here, we're just going to click them all. You wouldn't normally click them all, but that's what we're going to do. The different ones are just slightly different. So standardized is based on z-scores. The studentized is based on a t-distribution. Deleted is the difference between the adjusted predicted value and the original observed value. And then if you divide this by the standard error, you get the studentized deleted residual. So they're all different ways of measuring the same thing. They have different pros and cons. You can look in your textbook, or I believe Dr. Jackson will mention which one he likes the best in class. We're just going to get them all for right now. Now, here we want, under distances, we want Mahalanobis, Cook's, and leverage. So, for the leverage or hat values, we want those to be small. So, closer to 1 means that they have higher influence. Influence is essentially saying how much does this one observation change the entire model. So if we changed this one observation or got rid of it, how much would the predicted scores change? Obviously, we don't want one score to wildly change our predictions, so we want this value to be lower. Cook's is another value of influence. So again, we want the values to be less than 1. If it's more than 1, that's a concern. So remember, leverage, that's hat. If it's close to 1, it's more influence, so we want it as close to 0 as possible. Cook's, the rule of thumb is that greater than 1 is a concern. So for Mahalanobis, this is a more direct measurement. So leverage and Cook's distance, Cook's D, they are measures of influence, whereas Mahalanobis simply measures the distance from one point, from the predicted point to the observed point. And this value is based on a chi-square. Now, for influence statistics, we want we're just going to click off all four of these. So the DF betas, standardized DF betas, DFIT, standardized DFITs. Again, typically we wouldn't just click all of them, but we're going to just do that for right now. We want to look at what they all are. So these, similar to the distances, help to tell us, okay, how much would this model change if a single observation was removed. So if we took out one case, how much would the model change? Okay, so we're going to click continue there. Okay, next up, we want to look at the plots. To look at homogeneity of variance, linearity, and normality, we want to look at the residual by predicted graph. So what we're going to do here is we're going to ask for the Z predicted, put that on the X, and Z residual, put that on the Y. Now we're going to ask for both the histogram, norm probability, and all partial plots. If you wanted, you could have other plots as well. You would just click next, and then you could put in a new plot, but we're just going to ask for this one. Finally, under options, we can look at what you want to do for missing cases. We're just going to leave it as exclude cases listwise, but there are different options here. So finally, we are not going to look at style. We're not going to bootstrap. We don't need to bootstrap right now. As far as we know, remember, we're running this regression just to find if our assumptions are being met. So I'm going to click paste and then run the syntax. So, using the output that you get when you run it, so I want you to look for outliers. So, look at what the outliers are for Y, the predicted, on X, and influential observations. Again, when you run this syntax, that output that pops up isn't the only thing you need to look at. You also need to look at all of these new variables that you got. So it tells us in the label what they are. So we have these 5 different types of residuals, 3 different types of influence or distance statistics, and then all of these. So if I scroll to the end here, so these are just the normal residuals. Probably not going to look at that because really I want it to be either studentized or standardized. So I can see that, okay, standardized residuals is ZRE. Let's look at that one. Let's see, nothing here, nothing on that side, but here, oh look, we have a bunch of outliers. So you would go over to the start and say, okay, what vampire numbers are these? Okay, so it's 22, 34, 86, 43, so on and so forth. So what we want you to do before lab on Monday, fill this out. It might be helpful to make it into a chart form of, okay, what are the cases that seem to possibly be a problem, and then where are they problematic? So, for example, case 22, that looked like it was going to be problematic. Is it an outlier on Y? Outliers on X? Is it an influential observation? Combine all of your knowledge and come to lab on Monday ready to tell us what your guesses are for what the problematic cases are. And we'll go through finding each of those in class. Now, the final thing that I wanted to talk to you about before finishing up here is that this other file that is on Blackboard for you. Keep this file. You will need it. It is very helpful. Essentially, remember how I just went through all of those different variables and how there's the studentized residual, the deleted residual, the standardized, the deleted studentized. What do they all mean? Well, here it is. This is what those cutoffs are. So when you're evaluating whether something is extreme, use the cutoffs here. So this is how you should be basing your observations for lab. Okay, and that is it. If you have any questions, let us know. Remember, for lab on Monday, we want you to come to lab with your list of possible problematic cases. Bring that with you. Any issues that you had in doing this lab or any questions about, there's so many different assumptions for this. There's so many different values that we're having you use. There's a lot of new things here. Write them down. Bring them to class. I assure you other people will have these questions. There's nothing wrong with asking them. So bring them to class. Bring your answers. Bring your questions. And I look forward to seeing you all on Monday.